Good morning, good afternoon, and good evening, everyone. Thank you for joining us today and welcome to the DAS RCN webinar on engineering and urban seismology. I'm Casey Etterhold, a co-PI of the DAS RCN. IRIS is a consortium of universities and an NSF-funded science facility operating programs that enable earth scientists to perform advanced research in geophysics, particularly in seismology. This webinar will be recorded and archived on the IRIS Earthquake Science Presentations webinar YouTube channel. Should you have a comment or question as the webinar unfolds, then please clearly and concisely type it into the Q&A box, not the chat box, on your Zoom control panel. At the end, we'll read your name and question to the presenters. If similar questions have been asked, we may combine or skip them. If the webinar happens to crash due to Zoom or internet issues, we will reboot it. Just click the webinar link again. And automatic captions are available to be turned on and off on your Zoom control panel. Use of distributed acoustic sensing is rapidly expanding in our community, prompting the initiation of a research coordination network to facilitate workshops, tutorials, and other opportunities for sharing ideas and resources. This is one in a series of webinars on different topics within distributed acoustic sensing. I'm going to pass this to Biondo Bondi now to get us started.
Good morning, Casey, and thank you. Good morning, everybody. And as Casey correctly said, since some of you are around the world, good afternoon and good evening, and maybe even some good night. So I am Biondo Biondi. I am a professor in geophysics, and it's my pleasure to introduce two advanced PhD students at Stanford, with whom I have worked on DAS for several different applications for the past few years. And in particular, today, they will talk about DAS monitoring of bridges and urban traffic. The two speakers are Siyuan. Siyuan is a student in geophysics, a PhD student. I'm his advisor. And he has some civil engineering background because before joining us in geophysics, he got a master in civil engineering from Stanford University. And before that, he got his bachelor in civil engineering from Tongji University in Shanghai. The other speaker is Jingxiao Liu. He is a student in civil and environmental engineering at Stanford. His advisor is He-Yang No. Jingxiao followed He-Yang when she moved from Carnegie Mellon to Stanford. And we are very happy to have got He-Yang in our faculty and as a PhD student. And before that, he studied in China at the South Central University. So without further ado, I will let Siyuan and Jingxiao to present.
Okay, let me share the screen and Jingxiao will present the first part.
Yes. Cool. Okay. Good morning and good afternoon, good evening, everyone. And thanks, Biondo, for introducing Siyuan and I. I'm glad to share some of our work titled Distributed Acoustic Sensing Monitoring of Bridges and Urban Traffic. This work has been done by myself and Siyuan, advised by Professor He-Yang No and Professor Biondo Biondi, and from Civil Environmental Engineering and Geophysics Department. So the world is undergoing the largest wave of urban growth, resulting in over 50% of population living in urban area. So civil infrastructure plays key roles in connecting, protecting, and supporting this growing population. It is important for us to monitor critical urban components, including bridge health, roadway and railway traffic, in order to make our city more safer, more secure, more intelligent, more resilient, or more sustainable. Today, we will introduce a novel approach to monitor our bridge and also the roadway traffic. So bridge health monitoring is important because it allows us to detect bridge damage in early stages, which is essential for preventing more severe damage and collapses that may lead to significant human losses and business costs. However, there are over 500,000 of bridges in the United States, and over 22% of them were structurally deficient or functionally obsolete, and they need immediate attention and regular monitoring. And the number is still rising. As a result, to monitor this large stock of bridges, we need a scalable bridge health monitoring approach. Similarly, monitor roadway traffic help us to reduce traffic congestion and manage urgent emergency situations, such as car accidents. In addition, we can characterize vehicle running our road network, allows us to understand the traffic loads to our infrastructure for a better and informative urban planning. With more than 6.6 million kilometers road network, we also need a very scalable traffic monitoring approach. And the current practice for urban monitoring, including bridge health and roadway traffic monitoring, is manual inspection, which provides flexible and detailed assessment of the bridge and the roadway traffic. But it's not efficient because of high labor cost and delayed detection of the damage or accidents. For example, there are currently biannual inspection costs around $2.7 billion per year. And to reduce the labor cost and achieve a timely monitoring, we recently installed sensors in a dedicated way on bridges or roadways, like inductive loops or cameras, to automatically continuously monitoring them. However, this approach requires on-site installation and maintenance of sensors and equipment on every structure of interest, and only provides very sparse information due to the high cost. And recent mobile sensing method overcomes the on-site installation and maintenance challenges, but because of privacy and connectivity issues, using such approach at scale is very difficult. To this end, in this work, we are introducing a novel method aiming to address conventional urban monitoring methods drawbacks. Our system records dynamic stream response of bridge and of the roadway structure using pre-existing telecommunication fiber as distributed acoustic sensors. Specifically, an interrogator injects laser into fibers, which would have phase shift due to vibrations. And by measuring the phase shift or backscattering, we are able to measure the stream response along the fiber with up to 250 Hertz sampling rate and meter scale spatial resolution. This method is beneficial because there are millions of kilometers of optical fiber cables deployed around the world. Also, most telecommunication infrastructure has unlit dark fibers, and they utilize pipes and conduits installed on bridges or on the roadside to span rivers, roads, and to distribute it to households. Our interrogator can interrogate up to 100 kilometer fiber that can cover many bridges and roadways in the urban area. Therefore, we can efficiently and cost-effectively monitor bridge and traffic without on-site installation and maintenance, and without any interference to regular telecommunication signals. In particular, our system captures the vehicle-induced ground vibration and the structure vibration using the pre-existing telecommunication optic fiber cables. The dynamic components of the DAS signal captures the vehicle ground and vehicle bridge interactions. It covers the frequency band for bridge health monitoring and for subsurface imaging. Also, the quasi-static components of the signal captures the ground deformation due to the self-weight of the cars, which provides precise car location information for traffic monitoring and fiber mapping. And today we will mainly focus on bridge health monitoring and traffic monitoring. And I will firstly introduce the DAS for bridge health monitoring in detail. The main challenge of this method is the large measurement noise, mainly because pipes and conduits that carry cables were designed for bridge crossing instead of for stream sensing. Specifically, there are different types of coupling between the cable and the bridge. Like pipes and joints also very different, such as the anchoring hanger, clamps, or some were installed inside the prefabricated concrete decks. These differences results in large measurement noise and uncertainties of dynamic strain response from the telecommunication cable compared to well-calibrated and dedicated strain sensors like strain gauge FBG sensors. So to address this challenge, we constrain our estimation of mode shape functions with physical insight of the bridge dynamics in order to extract bridge damage sensitive feature, including natural frequencies, strain and displacement mode shapes. There are two key constraints I want to introduce here. In particular, since DAS measurement is dynamic strain, we can first estimate the strain mode shape of the bridge, which is proportional to the second order derivative of displacement mode shape. Therefore, estimating displacement mode shape requires one to double integrate the estimated strain mode shape. This double integration can be performed numerically or analytically. However, due to a large measurement noise, conventional numerical and analytical double integration method, for example, analytical double integration with a polynomial basis function, are often inaccurate, as the error would propagate in the integration steps. Therefore, we physically constrain the strain mode shape function with a homogeneous solution of it derived based on beam theory and bridge dynamics. In this function, d is the distance from the sensing location to the neutral axis, and lambda is the material property, related material property like Young's modulus, moment of inertia, and A, B, C, and D are parameters that can be evaluated with boundary conditions, including zero displacement values as supports, equal angle of rotation, and equal bending moment values as mid supports. With all these key constraints or the presupposed, we can physically constrain our estimation of the mode shape. Now let's proceed to introduce our bridge health monitoring system. And I will show you how the physical constraint mentioned above help improving our estimation. Firstly, we formulate this problem as an elemental strain state space model identification problem because it is a more compact and convenient representation for this multi-input, multiple-output system. In this system, we have X, that's the true strain dynamics of the bridge. Y is the measurement strain from the DAS system. A and C are system matrices. And W is the disturbance of stochastic input loads, including the traffic load. And V is the measurement noise. So we apply the stochastic subspace identification algorithm to estimate the system matrices A and C, given a set of output measurements from the DAS. We use this method mainly because it does not need nonlinear optimization techniques encountered by other methods, such as prediction error minimization. To estimate the displacement mode shape, in the next module, we fit the physics-guided shape function, as mentioned before, to the estimated strain mode shape, then conduct an analytical double integration on the fitted function to obtain the displacement mode shape. This method addresses the large measurement noise problem and improve the estimation accuracy with bridge dynamic constraints. To evaluate our system, we conduct a field experiment on a 50-meter long concrete continuous three-span bridge in San Jose City. It has two-lane, two-way traffic and also pedestrians. We also install conventional accelerometers as a validation system. As shown in the figure, we have 4 accelerometers. We have one on each middle span, and we have an extra one on the third quarter of the mid span. And we collected 10 data sets in consecutive 2 days in order to have a statistical study of our method. This shows our natural frequency identification results. As shown on the left-hand side, the blue curve, that's DAS measurement, power spectral density, x-axis that's frequency, y-axis that's the power spectral density magnitude. And the red curve that's measured by the conventional accelerometer. And on the right-hand side, we have the measured natural frequency error between the accelerometer and DAS system for the first 3 modes identification. As you can see, we successfully identified the first 3 modes at around 4.6, 6.4 nanohertz, and we achieve a very small error, which is 0.06 Hertz mean absolute error between the two systems. Our method also successfully estimates the first three modes stream mode shift functions in a meter scale, as shown in these animations. That's measured by DAS system. We have a very high spatial resolution. We are also able to estimate the displacement mode shape by fitting and double integrating the estimated stream mode shapes. To evaluate our estimation, we calculate the model assurance criterion, which is a metric that measures the mode shape consistency between the accelerometers and DAS data. This figure shows the distribution of model assurance criterion, aka MAC, values for the first three modes using our methods and two baseline methods, including numerical double integration, which is NUM shown here, and also analytical double integration with a polynomial basis function is a poly, the second box. And the MAC is bounded between 0 and 1, with 1 indicating fully consistency mode shapes. So higher means better. So our method, which is third box, outperforms the two baseline method by achieving a better consistency with the validation system using conventional accelerometers. And in part 2, Siyuan will introduce DAS work for traffic monitoring. You are muted, Siyuan.
Muted.
Okay, let me reshare the screen.
Right, looks good.
Yeah. Yeah, so in part 2, I'll share the using DAS for traffic monitoring. To demonstrate that the quasi-static signal of DAS can reflect vehicle motion, we conducted driving experiments with onboard GPS. The map here shows the driving path of our car at Sandhill Road that is covered by a section of the Stanford DAS2 array. And here our car was going south, and we made a U-turn, and we going north and make a second U-turn and going back to the parking lot. On the right-hand side, we can see the corresponding telecom fiber response. So showing the going south, the first U-turn, and then the second U-turn and going back to the parking lot. And using a DAS-based traffic monitoring can be promising, but there are still challenges to be solved. First one is that we observe like noise contamination. It's the DAS array not only record traffic, but record noises from various sources. And when there is a heavy traffic condition, we see interference among closely traveling cars. When two cars traveling close enough, their signals can overlap on each other, creating complicated patterns, limiting the effectiveness of detecting and tracking algorithm. So to address these challenges, we propose a machine learning solution. Specifically, we design a UNet model to perform a spatial deconvolution with a spatial wavelet here. So it's the wavelet we denoted as K, and it takes the quasi-static signals on the left-hand side, we denote it as Y, and it will output a sharp and localized deconvolved results shown on the right-hand side. We denote it as X. The output will shows the car trajectory. And the loss function we use contains two terms. First one is the data fitting term, which is spatial convolution between the spatial kernel K and the output, deconvolved output. It will take the difference between the reconstructed input, which is the convolution, minus the Y, which is the original input. So this is a data fitting term. The second term is the regularization term, which is the L1 norm of the output. The idea is to suppress background noise and make the deconvolved result sparse. As you can see, we don't need to provide any ground truth labels. So this is which makes the approach a self-learning approach. And now you may ask me why we don't perform deconvolution along the temporal dimension with a temporal wavelet. The answer is that we observe both from the field experiment and synthetic experiment that the spatial wavelet is more stable to speed change. As I can show you here, the top 4 panels are the signals of our own car traveling with 4 different speeds. The bottom 4 panels show the corresponding frequency and wave number spectrum. And you can see that the frequency component for the 4 different speeds is changing, indicating the temporal wavelet is speed sensitive, while the wave number components remain the same for the 4 cases. So this shows that the spatial wavelet is speed independent. So this suggests that if we perform deconvolution along the spatial dimension with spatial wavelet, the network will be more stable to speed change. To validate that, we train 2 models using the same data. So one model is a spatial deconvolution unit. The other model is a temporal deconvolution unit. And we evaluate the two models using a data set that is our own car with different speed. We first speeding up and then slowing down, as you can see from the left panel. And the second panel shows the results of the trained spatial deconvolution unit model. And you can see it outputs sharp and localized results regardless of speed change. The third panel shows the result from the temporal unit deconvolution model. And we can see that the results depends on speed. When the speed is fast, we see the result is more localized. When there's low speed, you can see the result is becoming broader. So this is less ideal. Lastly, in the last panel, I'm showing you a result from a conventional iterative deconvolution approach. So this is a signature deconvolution also along the spatial dimension. As you can see that the results are not as localized as our spatial deconvolution results. And also we observe some side lobes showing up here. Our spatial deconvolution outperformed the conventional deconvolution approach. I think the reason is that the UNet model can capture the spatial temporal information, while the conventional iterative decon is applied for each time step independently. And from these spatial deconvolution results, we can track the car trajectory by following the amplitude at each time step. And then we can perform a local beamforming algorithm along the trajectory to get a fast and accurate speed estimate. The bottom 4 panel shows the corresponding localized beamforming spectrum. We can estimate speed by picking the amplitude for each time step. So that will be our speed estimation with the black curve for each panel. And to validate our estimate, we install a speed sensor inside the car. And the speed sensor result is showing in as a red curve overlaid on the spectrum. As you can see that the result obtained from the spatial deconvolution result is matched. Sorry, can you guys hear me? I think
yes.
It's got frozen.
We can hear you.
Okay, cool. So as you can see that our spatial deconvolution has matched the red curve the best. And we compute the root mean square error for the 4 different cases. And we can see that we achieve the lowest RMSE score error, which is 3.4 kilometers per hour. So this makes our deconvolution model ideal or desirable. And our model can be especially important when there's under the heavy traffic conditions where multiple cars are traveling closely. And we can see traffic patterns more easily from the deconvolution than from the original qualitative signal. And we can zoom in here, for example. You can see that when the two cars traveling close enough, we cannot differentiate them from the original input, but from the output, we can see clearly there's two cars traveling close. And here is another case. We see two cars loading, their signal overlaps on each other. Hard to see from the quasi signal, but it can easily identified from the deconvolve results. All right. And we can also apply our spatial UNet deconvolution algorithm to signals from a large size vehicle to identify the axle numbers and to estimate the length of the vehicle. So here, the quadratic signal shows a signal of 18 meters 3-axle bus. And this top right panel shows the spatial deconvolution results, and we can see 3 peaks and indicating each axle. And if we measure the distance between the two peaks, it's around like 17 meters, matching the bus length. Well, from the temporal deconvolution and the conventional deconvolution, you cannot really see the axles. Lastly, we present you a demo for fine-grained traffic tracking and characterization. The triangular marker in the map shows the moving vehicle tracked by our system. The bottom figure shows the waterfall display of dust signals, and the colored curve indicated tracked vehicles. We put a camera at the end of this the dust section to capture the ground truth. And here shows the recording of the camera. As you can see that we successfully identified number of outbound and inbound vehicles, and we estimated wheelbase and car speed and the weight of the cars. In conclusion, we introduced an efficient and non-dedicated urban monitoring system, especially focusing on bridge health monitoring and traffic monitoring using the pre-existing telecommunication fibers with DAS technology. We overcome large measurement noise and uncertainty challenge in bridge health monitoring by imposing physics-based constraints on the mode shapes to estimate natural frequency and mode shapes. And we present a spatial deconvolution neural network to increase the resolution of traffic signal to better reveal traffic patterns and for fast speed estimation. And we showed a demo for fine-grained traffic monitoring and traffic characterization. With that, we would like to thank our collaborators, especially City of San Jose, OptaSense, City of Palo Alto, and Liebel Fellowship, and the Sustainable Built Environment and the UPS Endowment Fund at Stanford University. Thank you all for your attention. We're happy to take questions.
Yes, Dr. Wang. Bin Zhao, I was gathering that an assumption is that the normal mode frequencies will change upon bridge failure. How will you validate the predictive effect of a shift in mode frequency as to potential failure?
So although we cannot damage the bridge right now to validate in the real cases, the city won't allow us to do it now. But that's given by the assumption you mentioned. You are right. Like when we observe a large change of the natural frequency or local change on the mode shapes, especially stream mode shapes, that indicates some of the damage appear on the bridge. That could give a quick first alarm to the inspectors, then to take a close look of the damage like cracks or loss of materials on the bridge, loss of stiffness. But we did succeed using the mode parameters like mode shapes and natural frequencies in our lab scale experiments. Here, I hope maybe it won't damage the bridge, but we did some experiments by loading the bridge with different number of cars. So we use this method successfully identify how many cars loaded on the bridge. That reflect the change of the structure.
Okay, that's very good. So it's partially a screening device for when you will have a human inspection.
Yeah, that's a first alarm system.
Mhm. Thank you.
Thank you so much.
That's
So,
okay.
Paul, on the questions, Paul has a question for, I guess, for Yao. So, how was the fiber attached to the bridge?
Yes, the fiber was clamped on the bridge. It's not well attached. That's why we want to use the physical constraint to impose a constraint based on the bridge dynamics to reduce uncertainty or noise due to the loose coupling. It was coupled like every half a meter. So it's not like dedicated sensors, we can attach them very well. But we still get information of the interaction between the fiber and the bridge, the dynamic interaction. And by imposing the physical constraints, we can estimate the true strain measurements of the bridge.
I got one comment and one question from Andres Chavarria. The question is regarding to the bridge. So, what do you know what percentage of bridges have fiber, and who owns those fibers?
We don't know exact number, but as we observed, most of the urban bridges has a cable spanning the bridge because the cable also needs to span rivers, overpass roads, highways, and distribute it in different households. So most of the urban bridges should have the fiber. So that's why it's a very scalable method in the future to monitor bridge without any installation of sensors.
Thank you. So Andres has another comment, and that is for the presentation by Yingxiao. He's talking about that the separation of cars is probably a meter or two, and you can play with the decreasing the optical gauge length to about 2 meters to be able to facilitate the separation of vehicles when they are traveling together. So that probably could help, and you should consider that. I do have a question for you. Oh, Joe has a question, so please, Joe.
Yeah, I also had a question about the bridge. I'm very curious about the physical constraints and how you came up with them. Can you talk about the procedure that you follow when I assume you have to go to each of these bridges and come up with some sort of structural model. Can you talk about that process and how that works?
You mean the numerical model of the bridge? Do we build a numerical model of it?
Right. So maybe I misunderstood, but your physical constraint that you have is based on your mode shapes.
Yes.
And to get those mode shapes, you have to have some structural model of the bridge. And so I'm curious how you go about assessing that structural model out in the field.
So that's based on theoretical model of the bridge. At least we know the drawing of the bridge. We know the shape of the bridge. We can design the constraint. And the constraint include two parts. The first part is the double integration relationship between strain and the displacement mode shape, strain mode shape and displacement mode shape. So we know because that's measure strain, but we also want the displacement mode shape, which is very sensitive to the damage. So we need to do the double integration. That's the first constraint. And the second constraint is the mode shape constraint. For strain mode shape, we have some homogeneous equation that described by beam dynamics, bridge dynamics, and we fit our dust data into the homogeneous solution of the bridge. Let's give the constraint to the dust data that reduce the uncertainty of the signal. And we don't need to go to every bridge to get the local measurement, field measurements in order to constrain the physics. That is based on the theoretical drawing of the bridge and the beam theory, also the bridge dynamics.
Okay, so if I understand correctly, the assumption is that all of these bridges can be modeled by effectively beams, and you're not taking into account any sort of complexities due to piers or the abutments or things like that. Is that right?
It is dangerous to say every bridge can be effectively modeled by homogeneous beams, but we try to simplify the model and give very principal constraints. That's a key principle of the bridge. But we do have different type of bridges. They have different cross sections, different span, and different forms like suspension, cable stay, or different type of bridges. They definitely have very different constraints we need to impose, we need to consider. That's what we want to do in the future.
Great, thank you.
So we do have one more question for Dr. Wang, and then we are going to stop the questioning so we have an opportunity for the next presenter to present. So Dr. Wang.
Yeah, Siyuan, I was very impressed by your ability through deconvolution to identify the number of axles and the weight of a vehicle. So I was thinking of traffic enforcement of trucks going by way stations. You should be able to identify the weight and number of vehicles that they go right by a required way station. But for what distance do you think you could track an individual truck that failed to stop at the way station in terms of giving a ticket to that particular driver?
Yeah, I think we don't have internet collaboration with the police to share the results with police department yet. But I think for now, our observation is that the truck is 20 meters or more away from the fiber. We can capture that very clearly. As a car, especially for heavy trucks, the signal is very strong. But yeah, we don't know like what the distance limit would be yet. Yeah.
Okay, thank you. It's just an application.
Yeah. For motion in way in motion.
Yeah. Thank you so much. Thank you so much, Jingxiao and Siyuan, for very interesting presentation. Actually, I have a couple of questions for you that I will send you by email. But they were very interesting. By the way, also, Biondo, thank you very much for identifying this presentation. You are right. These are very interesting topics that you guys are working on. So thank you so much. So I haven't introduced myself. My name is Dante Fratta. I'm with the University of Wisconsin-Madison, and I have the honor to present the next presenter. This person is Joe Vantassel, and he's a brand new assistant professor at Virginia Tech. He earned his bachelor's in civil engineering from RPI in 2016. And during his study, he put emphasis on geotechnical and structural engineering. After his undergrad, he went to University of Texas Austin, where he got both master's and PhD in the area of geotechnical engineering, in the general area of geotechnical engineering, and graduated in 2018 and 2021. And actually, I met Joe in 2021 with the area UT Austin decided to purchase a DAS interrogator for use of the community. And I know that Joe was instrumental in evaluating multiple systems during the decision-making process when they were doing the purchasing. Starting in 2022, he worked as a researcher at the Data-Intensive Computing Group at the Texas Advanced Computing Centers, and working with problems related to big data. And people who work with us, we know all those issues related to big data. So this is Joe is very well prepared to be able to help us tackle these problems. And in January 2023, as I said before, he started a tenure-track position at Virginia Tech in the group of geotechnical engineering, and he's going to be working mostly in the area of subsurface imaging. So with that, Joe, the floor is yours. Thank you so much.
Thank you, Dante, for the introduction and the invitation to come and speak. So today I'm going to be talking about the importance of wavelength when we're using DAS for near surface applications. As Dante mentioned, my background is in near surface geophysics and near surface site characterization for engineering applications. However, before I go ahead and get started in the actual presentation, I just want to acknowledge that this research that I'm going to be talking about is just a piece of a larger and ongoing effort that started in 2021. It's actually when we met, Dante and I had met. And so far, it's produced 2 journal papers. There's 2 more on the way. There's a conference paper, a published data set, and a poster. So all of this is really spawning out of this interest of the NERI at U-Texas site in purchasing a DAS interrogator, and some of the field tests that we're doing out at the NERI at U-Texas site down here in Austin, Texas. So a little bit about what this study is on. So this study is really focusing on, can DAS replace geophones specifically for near surface characterization? And more specifically, we're going to be looking at things in the context of the multi-channel analysis of surface waves, which is, of course, a very common technique for making measurements of site stiffness, which is, of course, important for engineering applications, for site characterization, void detection, all of these things that are of interest related to the engineering side of the work that I do. So for those who may not be familiar, we'll start with a brief overview of MASW testing. And there are three different parts of MASW testing. The first is the acquisition, and then processing, and then inversion. And I'll talk about all three of these very briefly. The first is, of course, the data acquisition. Here I'm showing a traditional acquisition with geophones. We have geophones spaced along the ground surface every 2 meters. And we have 24 of them, which gives us an array of 46 meter length. And we're recording here ½ a second of data. And really, the type of data we're interested in here is data that's rich in surface waves. That's what we're looking for with this testing method. And the way we go about doing that is we typically hit on the ground with some sort of source, typically a sledgehammer, but you can use other more powerful sources if you have access to them. And as you can see here, I've just highlighted that you can see the surface wave has a lot of energy in it, and therefore it kind of makes it ideal for trying to capture at the surface. Once we have that experimental data in the time distance domain, then we want to do a 2-dimensional wave field transformation to convert that over to frequency and phase velocity. We can do that using a variety of different wave field transformations. I show just one of them here. This is the Park transform, or the phase shift transform, whatever you'd like to call it. And the result here is a image which is showing wave field power as a function of frequency along the X and phase velocity along the Y. And the important thing to note is that these waves are dispersive, meaning the velocities are changing as a function of frequency. And we can go through and pick these phase velocity peaks to get a measurement of our site's modes of propagation. Here, we're just showing the fundamental mode, Rayleigh wave propagation. But as you'll see later on, you can have higher modes, and things can get correspondingly more complicated. But of course, this phase velocity is not what we want for the end result, not for site characterization. What we really want is some sort of layered Earth model, which is defined by the thickness of each layer and the shear stiffness, shear wave velocity of each layer, as well as the mass density and compression wave velocity, although those terms have a much lower impact on the corresponding dispersion. The way we go about doing this is by solving this complex inverse problem, where we will assume a 1-dimensional model. We will calculate its theoretical dispersion. We will compare that to the points we measured out in the field, and then modify this model accordingly, and we'll try to get a better match between the two. Of course, it's nonlinear and non-convex, making it ideally suited for global search optimization algorithms. And so, with that brief overview, let's go back to our original problem, which is, can DAS replace geophones at the near surface? And I want to start by highlighting some examples from the literature, examples that were available to us back when we started looking at this problem. The first is from Galancomas, 2015. They showed that you can get reasonably good agreement between geophones and DAS over a pretty decent frequency range. Here they're using active source MASW, like I was laying out on the previous slide. But one thing we note is that the DAS dispersion is band limited. We see that when we go to higher frequencies, we have geophone dispersion data, but we don't have DAS dispersion data, which is problematic at the near surface, because those higher frequencies, which correspond to shorter wavelengths, are really what's going to tell us about what's in the top few meters of the subsurface, which is important, of course, for applications I'm interested in. The next example is from Song et al. 2020, where here we have we observe a systematic bias in the DAS data, about 10% higher velocity than what we get from geophones. And given that typically our error or our uncertainty in our MEMASW measurements is about 5 or 10%, this is pretty significant. And then finally, in 2022, Vantassel et al. Had published a comparison between DAS, geophones, and accelerometers. And we see that over a certain frequency range between about 7 and 10 hertz, all of those agree very well. But then below 7 hertz, we start to see significant difference between the two, with now DAS being biased to lower velocities. So from these examples, we decided that further investigation was warranted to sort of better understand what are the things that influence good quality dispersion data, or dispersion data that's of equal quality to geophones, and what considerations can we make to improve the fit at all sites. So to go about doing this, we have the experimental site that was established at the Nereid U Texas Hornsby Bend test site, which is located down here in Austin, Texas. And we deployed 200 meters of fiber. So that's shown in this brown line here. And adjacent to that, for this experiment, we put a geophone array. So we have 94 meters of geophones shown in this dashed blue line. And we had geophones every 2 meters. And then off the end, we excited both of the arrays simultaneously using source positions between 5 and 40 meters off the end. And then to make comparisons back to some sort of invasive measurement, we have CPT measurements at 3 different locations along the geophone array. So regarding the DAS fiber installation, we actually installed 2 fibers alongside one another. We had the NANZ, which is a strain sensing cable, and then an AFL, which is a tactical type buffer cable. Both are sensing inline along the alignment of the array. For the actual physical installation, started by creating a shallow trench, a few centimeters deep, then placing both of those cables alongside one another. It's a bit hard to tell, but there are in fact 2 cables there. And then of course, making sure that they are in there as best they could be, as straight and as tight as possible. And then carefully backfilling over the top, and then compacting the soil to ensure good coupling between the soil material and then the outside of the fiber optic cable. For the DAS acquisition, we were using the OptiSense ODH4 with a 2-meter gauge length and a 1-meter trace separation. Sensing here is proportional to strain. And for post-acquisition processing, we downsampled the data to 1,000 hertz and applied a 3 hertz high-pass filter to limit any artifacts down near DC. For the geophone installation and acquisition, we were using Geospace GS11D 4.5 hertz phones. We deployed both vertical and horizontal phones. For this presentation, we're only going to be talking about the horizontal phones, because those are the ones that were oriented in the same direction as the DAS, right? So they were oriented horizontally, but pointed inline. So they should be measuring the same component of the Rayleigh wave that the DAS is, and therefore their dispersion data should be directly comparable. And the geophones here are sensing, of course, proportional to the particle velocity. For seismic sources, since we were using Nereid U Texas equipment, we used two of their vibra size as well as an instrumented sledgehammer. The first fiber size that we used is the T-Rex, which is a large fiber size that can shake in both the vertical and inline directions. We used a linear chirp from 3 to 80 hertz over 12 seconds. And the vertical force output of T-Rex is about 270 kilonewtons, and then in the inline direction, about 130 kilonewtons. Now, Thumper is a bit of a smaller fiber size, but can shake up to higher frequencies. So we used a linear sweep from 5 to 200 hertz over 12 seconds, and we can get a force output about 27 kilonewtons. And then finally, a sledgehammer source, which is an instrumented sledgehammer. So we were able to record the source signal, and of course, hitting in the vertical direction. Records typically on the order of less than 0.1 seconds, and a force output of about 20 kilonewtons. But of course, using a sledgehammer is more variable than the fiber size, and depends on the operator and how well things are coupled to the ground. So if we go and we process all of this data, and by all of this data, I mean we had 4 different source positions with 4 different sources: T-Rex in the vertical and inline, and then Thumper in the vertical direction, and then Sledgehammer in the vertical direction. And then we also used 2 different wave field transformations. So we combine all that together, we get about 32 measurements at each frequency phase velocity, which we can use then to plot these, what I call cloud plots, where effectively we're looking at the density of dispersion data as a function of frequency along the X and phase velocity on the Y, where the darker color is indicating higher density of data points. And what becomes apparent is that we see these 3 modes of Rayleigh wave propagation, at least 3 clear modes. There are potentially higher modes here that we could have selected, but opted not to for this study. And we can see that if we compare panels A, B, and C, which have the geophone data on the left, and then the NANSI cable data in the center, and the AFL cable on the right, we can see that we get good consistent dispersion measurements for all 3 of those modes over a fairly broad frequency range. However, we observe something going on down at higher frequencies and low phase velocities. So these are our short wavelength measurements. And this is reminiscent of what was observed by Gao and Comas, where their DAS data did not extend to the same short wavelength, same high frequencies that their geophone data did. That's what we're seeing here. We see that the geophone data is getting right about down to 2 hertz, which is getting close to our receiver spacing. And yet we don't see that same data in the NANSI and AFL. So one way to look at this is to consider that we have a wave traveling down our DAS array, which of course we can decompose into a summation of sinusoidal waves using Fourier analysis. We can model one of them using a function of this form, where U here is our displacement field. And we can define our strain as just a partial derivative of that with respect to X, and then we can define the strain we'll measure with DAS as just the integral of that exact strain over the gauge length. And if we divide those out, we get this nice transfer function, which kind of explains to us how DAS is going to behave as compared to the exact solution. And if we plot it, what we'll see in terms of its error in its phase and then an error in amplitude, we can see a sharp phase change at about a wavelength equal to the gauge length. And then in terms of amplitude, we can see that as our wavelength is approaching our gauge length, we start to get a lower and lower amplitude, eventually hitting 0 or right around the gauge length there. So what this is telling us is that as our wavelength that we're measuring is approaching the gauge length, we're not going to be able to make high quality measurements, which of course is consistent with what we were seeing experimentally. And if now we go back and say, well, how does this compare to the experimental observations I kind of started our discussion with? So for the same 3 studies here, now I've plotted the gauge length that they use at the wavelength. So here is a gauge length of 5 meters. So this is a wavelength of 5 meters, effectively, this black solid line. And so what we see in this study, in Gallicoma's study, is that we don't have any dispersion data that extends near or below it. So this is kind of giving us some indication of why perhaps their data was cut off at about 20 hertz. And same thing for the other 2 studies. In Song et al., we can see that the quality of the match here between the DAS and the geophones degrades as we get below the gauge length. The gauge length here was 10 meters. And then finally, for the Lancel et al. Study, we see again, we don't have any data near or below the gauge length. This one's a little bit more difficult to say because there's also no geophone or accelerometer data. So it's a little bit more difficult to say it's purely a gauge length issue. It could very well be some other complicating factor. But we certainly observe that dispersion data quality is decreasing at or below 1 gauge length. And of course, we can compare this now with experimental observations we made at the Hornsby Bend test site, where here we compare, on the left is the geophone data. This is for the T-Rex shaking vertically 5 meters off the end of the array. And so this gives us a sense of ground truth or state of the art right now, if we consider geophones the state of the art. And we compare that with the NAN-Z cable with a 2 meter gauge length. 2 meters here is plotted down with this white line. So you can see we're very far away from the gauge length, and therefore we wouldn't expect any limitations of the dispersion data due to that effect. And in fact, we see if we compare A and B, that we get dispersion data that's essentially identical. We have data up to about 30 hertz in both cases. However, if we repeat that data acquisition, T-Rex is in the same position it was. It's doing the same type of vertical shaking it was doing before, but now we change the interrogator unit to now have a 10 meter gauge length. We can see that we lose that data below 10 meters. So now you can see if you compare panel C with panels A and B, that we have effectively lost data, or we're not able to resolve surface wave dispersion at or below this 10 meter wavelength here. So a really important consideration when using DAS to make near surface measurements where those short wavelengths are really important. So if we go back now to the main problem we were originally interested in was, can DAS replace geophones? Here we show a comparison of the dispersion data. So if we recall the cloud plots I was showing earlier, those were kind of showing all of the data. Here, what I'm showing is the data that has been cleaned up and organized into plus or minus 1 standard deviation ranges for the geophone and then the 2 DAS cables. What we can see is that these areas here are all overlapping, which are indicating that the geophone and the DAS data are all very consistent with one another, and that we're getting very good consistency for both the fundamental and the higher modes. You'll note that the second higher mode agreement is not quite as good as for the lower mode. However, if you recall from those cloud plots, the data gets more complicated as you start going to higher modes. And so some of this is just the influence of more complex data. And again, we very clearly see that effective gauge length here where we don't have overlap, and we see that the DAS data is getting cut off at a shorter frequency, or a lower frequency, longer wavelength rather, to the geophone data. So right, the geophone data is being extended to those shorter wavelengths where the DAS is being cut off because of the gauge length effect. If we kind of continue this analysis forward and we take one of those data sets, since they're all very similar, it doesn't make much sense to invert all of them. But if we took one of those data sets, in this case, we took the NAN-Z data set, Here we're showing in black is the mean and plus or minus 1 standard deviation dispersion data for those 3 different modes. And these colored lines here are showing the inversion results. So these are the theoretical fits to that data. And for doing this, we use the uncertainty consistent procedure that has proposed in 2021 that we've now extended to higher modes. The different colored lines are for different parameterizations. So we fit the data using 3-layered model, a 5-layered model, a 7-layered model, and a 9-layered model. And this is giving us a way of quantifying sort of our bias variance trade-off as we're fitting this dispersion data here, where the 9-layered model will likely fit the data very well, but may have high variance, and the variance may not be realistic, whereas a 3-layered model will not fit our data quite as well, and will have some bias, but will have much lower variance. So to do this inversion, so each of these parameterizations were inverted 250 times, and that gives us our 250 different estimations of the data and its uncertainty. Those were all searched 300,000 models. So we looked through 300,000 one-dimensional models for each of those realizations. So in total, we searched 300 million layered Earth models to come up with these final fits that you see here. And to do that, of course, required supercomputing. So we used resources from the Texas Advanced Computing Center provided through DesignSafe. And here are the resulting shear wave velocity profiles. So in panel A, we're showing shear wave velocity in meters per second as a function of depth, and we're showing it down to 50 meters here, or 30 meters rather. And this sort of cloud of velocity profiles that you're seeing is giving you a sense of the general trend that the velocities are increasing with depth, but also a sense for the uncertainty that we have generally growing with depth. And we see that the Hornsby Bend site is a soil-like material kind of extending down into a gravelly, weak rock type material, which is consistent with what we would expect from the local geology. In panel B, to make things a little bit less cluttered, we're just showing the medians, the median from each parameterization and the median across all of the profiles, and comparing those with the CPTU measurements, or rather correlations with the CPTU measurements. So we take our CPT measurements from the field, we correlate those with shear wave velocity, and that's what's being shown here with these pink lines, which is showing reasonably good agreement over the top 10 meters. And then finally, panel C is showing our uncertainty in shear wave velocity as a function of depth, as being the log normal standard deviation of shear wave velocity. So if we go back to panel B, briefly, this is kind of tying back to the fact that not only is the dispersion consistent between our geophones and the DAS, but also that by inverting that data, we are getting shear wave velocity profiles that are consistent with other measurements that can be made at the site. And so with that, I want to acknowledge the financial support from the National Science Foundation and the computational support from DesignSafe Cyber Infrastructure and the Texas Advanced Computing Center. And then offer a brief summary of what we accomplished here. First, we showed that high quality multi-mode dispersion data can be extracted from DAS measurements. And by high quality, we mean that the DAS dispersion can be identical to that acquired by geophones. Second is that the DAS gauge length needs to be selected carefully to ensure sufficiently short wavelengths can be measured, and that we recommend this be done on a project-specific basis. If you're working on a project that requires short wavelengths, then you need to make sure that you're using a sufficiently short gauge length to accompany that. The third is that the DAS-derived VS profiles compared to those correlated with CPTU measurements, again, showing that consistency with other measurement approaches. And then I'll highlight that this data set, both the DAS and the geophone data, has been archived and made publicly available through DesignSafe, and the DOI will bring you there. And then the full paper that talks about this, that covers what I covered in this presentation, It has been published earlier this year in the Journal of Applied Geophysics. So with that, thank you very much, and I look forward to any questions.
Thank you, Joe, for the very interesting presentation. I fully enjoyed it. Dante has to go and teach a class, so I'm taking over the responsibility of moderating the session. And so Joe's presentation is open for questions. You can raise your hand like Herb did. So, or you can also open your mic and ask directly the question or in the QA. Herb?
Okay, Joe, thank you very much. That was a very nice presentation. My question is, did you consider using ambient noise instead of active sources? And if you were to use ambient noise, do you think you could get results comparable to the active source results?
Yeah, thank you for the question. We did not use ambient noise out at the Hornsby Bend site. I think perhaps at lower frequencies, we would be able to. There's a highway not too far away that we might get some good ambient noise data. However, the Hornsby Bend site is fairly isolated. It's out down by the Austin airport, for those of you who've flown in, kind of in like a farm type area. So I don't know how well we would do at these higher frequencies, but it would definitely be something interesting to look at. None of our deployments are really long enough to acquire enough ambient noise data to know, but perhaps an area for future work.
Yeah, I was thinking of urban areas where you might want subsurface profiles, and there would be greater ambient noise sources. Okay, thank you.
Thanks, Herb, for the question. We do have a question in the Q&A. We'll read it out for the whole audience. It's for Mahamud. Thanks for the presentation. Can you comment on the similarity and difference between the two types of cable used? How does the cable construction may affect the sensitivity and the phase velocity measurements?
Yeah, so I'll caveat what I'm about to say by saying we only looked at two cables, right? So we only looked at the NANSI and AFL, so definitely not an exhaustive search of cables. However, we did not see any differences in the dispersion data. Even this figure here, you can see the NANSI cable is in this brownish color and the AFL is in the greenish color. And by and large, we see consistent dispersion measurements as well as consistent uncertainty on that dispersion from both of the cables that we looked at. So we're inclined to believe that given proper installation and good coupling with the ground, that the cable may not be too critical to making good measurements of phase velocity. But more research would only be able to tell for certain.
Thank you. Mohammed has a follow-up question. Did you look at the reflected waves?
Yeah, so we only performed surface wave analysis here. So when we're looking at the wave field transformation, those are really going to be picking up on the surface wave. The vast majority of the energy that's going to be propagating down our line, it's about 70% surface waves. And so therefore the wave velocities we're going to be estimating are those of surface waves. So with that, we did not look at reflected waves, although further analysis, the data is publicly available. So if that's something you were interested in, that's something you could certainly go and look at.
Thank you. There are two questions. One is another follow-up from Mahmoud. So please, I will ask it ahead, give a quick answer. What about the amplitude sensitivity and directionality for the two cables?
Yeah, so with regard to amplitude sensitivity and directionality, as they affect dispersion, we don't see any direct differences. One detail of that is while we're doing surface wave processing, we make a conscious effort to do normalization in the wave field transformation domain in order to mitigate the amplitude differences. So let me explain what I mean by that. So the geophones, for example, are measuring in units proportional to velocity, whereas the DAS is measuring in units proportional to strain. And then, of course, there are conversion factors and approaches that you would need to do to either convert one to the other and correct to some physical unit. Like if you wanted everything in terms of strain, then you would need to make the appropriate corrections. Or if you wanted to see everything in centimeters per second, you would need to make the appropriate corrections. We did look into that. However, ultimately, what we found is if you perform frequency-dependent normalization, it doesn't matter the units that you're looking at with regard to the data that you're putting in. So that way I can process the geophones in the exact same manner as the DAS data, and we will see the same wave field, same dispersion result from that.
Thank you. So there is something now talking about sensitivity to the geophones from Leila. Which geophones are used to compare the dispersion curves from DAS and geophones? Are horizontal geophones in line with the fiber cable direction?
Yeah, exactly right. So we're using horizontal geophones. They're 4.5 hertz, and more specifically, they're GS11D from Geospace. And they're oriented horizontally and in the inline direction. So they're measuring the same horizontal component of the Rayleigh wave as the DAS is. So making these directly comparable in terms of their dispersion.
Thank you. Paul has a question now on the sources, I believe. Did you shake at different load levels? I'm interested in any possibility of detecting nonlinear soil properties.
Yeah, it's an interesting question. For this study, we did not specifically shake at different strain levels. However, because of the limitations of the equipment, by using the sledgehammer, the thumper, and then the T-Rex, all of those chirps are done at different force outputs. However, for any given one, we did not change the load. If that makes, hopefully that makes sense. If that's not clear, I can follow up. But there are different load levels, but there's also the kind of confounding variable that the waveform will also be different as well, the input waveform.
We have a question from Christopher. Hi, thanks for the nice presentation of very impressive results. In the beginning, you indicated that previous studies had noticed a bias to lower phase velocity of DAS recording at low frequencies. Did you find an explanation for that, or could you reproduce these results?
No, we did not see bias at low frequencies. However, we were also not able to make low frequency measurements to the same level as what was able to be done by the Lancel et al. Study. So part of it is we weren't able to observe frequencies that low, so we weren't able to properly investigate what causes there may be for that bias at low frequencies.
Thank you. I don't see further question on Q&A. I will encourage you to ask more. I do have a comment or question that your studies that obviously the gauge lengths, there are many trade-offs when setting up the gauge lengths that have to do with signal to noise and distance that you may want to interrogate in terms of a cable length that is related to signal to noise. But one of the things that your studies made quite clear to me is the importance of the higher modes. Since the higher modes, they do have a higher phase velocity, and so that's at the same frequency, they are less affected by the gauge length. I think one of your other experimental results, not only the theoretical one, shows that. So do you have any comments about the opportunity to improve the resolution by looking after the higher modes even more than we were with geophones?
Yeah, higher modes can be complicated in the fact that it's often hard to excite them at a particular site, and you'll even see or seen in the past that certain source positions or certain types of sources will excite those modes more effectively than others. So it's rather interesting. So whenever you have a higher mode, of course, it's more data, which helps with your inverse problem and getting a more unique solution. It's still non-unique, but it's somewhat more constrained. But yeah, there is potential to utilize those higher modes as additional sources of information. And as they're less affected by gauge length, perhaps that presents an opportunity for the future.
Thank you. Andres asked a question now on the Q&A. Can you comment on the potential for strong ground motion analysis?
Yeah, so I haven't done any active work on looking at using DAS for strong motion acquisition. However, given the quality of the data that we were able to see at these very small strains, right? These strains are like 10 to the minus 5%, something like that. They're very small strain. We see promise in being able to extend up to higher strain. Of course, I think there will be some complicating effects as we're actually, potentially plastically straining the cable itself. But I think it's an area that could certainly be an interesting area of future work.
Thanks, Joe. I don't see any other questions. Please, while that I'm thanking everybody, you may able to ask another question that comes in your mind. Or Herb, should I pass on the baton to you as a MC?
Yes, I can close the webinar. I want to thank both Dante and Biondo for moderating, and to Siyuan, Jingxiao, and Joe for their presentations today. The recording will be made available on the IRIS Earthquake Science webinar playlist. If you're interested in future DAS webinars, please join the DAS mailing list and check out the DAS RCN website. Thank you again for joining us for this webinar.